Good morning, this is your Stats Sensei, and we're going to be talking about running hypothesis tests and confidence intervals for linear regression using data. Now, most likely this information is going to be coming from your table, and also I have to warn you that some of the things that we talk about probably not likely to show up on a free response, but likely to show up on a multiple choice. So first off, we always need to define X and Y in context. So here we have something else to define. So your X variable and your Y variables. We need to write your hypothesis, which is going to be beta 1 equals 0. And the alternative is beta 1 does not equal 0. And yes, you have to have the 1. All right. Because beta 1 represents your slope and beta 0 represents your y-intercept. We need to define beta 1 in context. Basically, the change we expect to see in y for every 1 unit change in x. And we need to say whatever our y variable is and whatever our x variable is. We need to write our conditions. So linear scatter plot. And we'll look at that when we actually run it. We need independent observation. N needs to be less than 10% of the pattern. No pattern in the residual plot. Normal distributed residuals. Equal variance, which is called homoscedacity. And what that looks like is earlier in one of our other videos, we looked at residual plot, and this would be having homoscedacity. There is no change in the variation. This one here is not homoscedacity or no homoscedacity because we have a change in the variation. All right, the change in the amount of the way the residuals go. All right. And of course, we need to have a random sample. Now, the reason it's in this order, which is a little bit different than the way I normally go, and you can change your order, is because it kind of spells out liner, L-I-N-N-N-E-R. All right, and that might help you remember it. But the fact of the matter is, these are things that are likely to show up on a multiple choice, but not on a free response. All right. So the equation, really, this is probably not that important. I've never seen it show up. This is extremely important. So what is that? That is the slope that we calculate from the sample divided by the standard error of the slope. All right, so once again, slope over standard error. And remember, they're likely to give you both this information, all right? It's going to show up on the table. We're going to enter the data into L1 and L2, which I've already done, calculate, and state our decision. Our p-value is blank. We reject a null. There's sufficient evidence at alpha equal point to suggest the true population is not 0. There is a linear relationship between whatever x is and y is. Then, of course, we fail to reject, in which case we're saying there is not a linear relationship. So let's look at this. Once again, we're working with the same information from the problem that we've been working on, where we had all the data on airfare. And that data, just in case you haven't entered it, is on page 246. Here it is real quickly. Once again, you can run this through the calculator, and here's your check values to make sure that you have good data entry. All right, so make sure you have that entered, and then we're going to run based on that information. So using the data from the airfare and distance scenario, perform a hypothesis test when alpha level of 0.05, determine whether or not the slope is significant. Well, the very first thing it said on our recipe was we need to define our X and Y in context. So when X was our distance traveled in miles, Y is the airfare, the fare charged in dollars. Our beta 1, so this is writing our null and alternative. So the null B1 equals 0, the population slope equals 0, the population slope does not equal 0. And this is 95% of the time always going to be a not equal for this. So there is no linear relationship between X and Y. There is a linear relationship between X and Y. I recommend you write this out for yourself so that you keep it straight in the middle of the test. It just seems to help students do better. Required, technically not, but seems to be very, very helpful for those who do. All right, what is our slope? Because that was one of the next things, is we had to define our slope in context. The expected increase in airfare for every 1 mile increase in distance traveled, or the change in airfare for every 1 mile change in distance traveled. Our conditions, random sample. Technically, it was not given, all right? So we're gonna have to assume that the data was representative. The scatter plot. Well, we actually created the scatter plot in an earlier video, all right? We did that in an earlier video. We're like, you know what? There is an upward trend of the data. And if there's an upward trend or a downward trend, if you can sit there and kind of guess to a line, then it's linear or reasonably linear or linear enough to say the data is linear. Residual plot must be random. And we looked at that in just a moment ago when we said, and here's our residual plot for this one. All right, which we've already done in a previous video. If you need to, you can go back and see that video. The box plot of the residuals show no outliers and are reasonably symmetric. So basically, I would need to calculate my outliers, calculate my residuals, and real quickly, we'll do that. Stat, edit. Then we go, I went up to L3. And by the way, you know what? I should run this whole thing, stat test, linear regression t-test. You have to do this in order to get the residuals. Alpha trace. All right, so I've run everything. I'm gonna go to stat edit, go to the top of L3. In this, I'll press second, followed by the stat button or the list button, and I'll find my residuals. Press enter, and it populated all my residuals. All right, so I need to do a box plot of that. First off, we'll go ahead and do the scatter plot. So I went to second stat plot, and I'm going to drop down and do the scatter plot, which is the first graph. And my X list is an L1, my Y list is an L3. I can press zoom 9, and there's a plot of my residuals. So there's my residual plot. And if I were looking at my scatter plot, second stat plot, the scatter plot, same thing, but L2 instead of L3. There's a residual plot with the line of best fit going through it. But we need to check to see how the box plot of the residuals looks. So second stat plot, we're going to drop down till we get the box plot showing outliers. But since it's the residual plot, this needs to be L3. We'll press zoom 9. Oops. Apparently I didn't switch things over. So second stat plot. Yeah, I did not hit save. On the box plot, you have to press enter. There, it's now selected. You should be good to go now. And my X list is an L3 because that's what I want to check, the residuals. Zoom 9. And there it is. And it's a little stretched out, but not too bad. And you can use the trace feature to get all of the important values and write those down. Okay, so we've checked the conditions. It looks like we're good to go. All right, so then we need this information here. I'm going to tell you they're not going to have you calculate that. They're going to give that to you from the table, and they will give you that standard error. You're like, well, gosh, Mr. Spencer, where does standard error come from? Well, on the table, here's the standard error of the coefficient, standard error of the slope. There it is. All right, so this divided by this equals that. So it equals the 3.86. And once you have that value, second vars TCDF, lower bound was 3.86 because once again, we got a T statistic of 3.86. So we're going this way, T is centered on 0. But because this was a not equal to, we also have a lower, which is why we have to have the 2 times in front. Multiply that by 2, and I get 0.00138 or 0.0014. Because we actually had all that information in the calculator, we would have gone stat test, linear regression t-test, and our p-value is shown right there. Okay? So how do you write your conclusion? This is important. Our p-value is 0.0014. which happens to be less than an alpha 0.05. So we reject the null. So there is sufficient evidence that alpha equal 0.05 to suggest the true population slope is not 0. When we say that, what we're really saying is there is a linear relationship between airfare and distance traveled. And you need to have both of these statements. There is or there is not a linear relationship between y and x or x and y. But you need to make sure you have that included. All right, so that whole thing would be your conclusion. All right, looking at a confidence interval. I'm going to blow through the requirements because we've already talked about defining x and y, et cetera, et cetera, et cetera. The part that we have to worry about that we changed is we need to know how to calculate t star. But once again, this is slope from the sample plus or minus t star SB. Well, t star is still going to be 1 minus the confidence level divided by 2, but you're going to need to use degrees of freedom of n minus 2. All right? Well, we have all of our data entered into the calculator already. And I'm going to go ahead and run this thing, just see what happens. So stat test linear regression t interval. My data is L1 and L2, and let's just see what they asked for. Use the data to form, use the data from the airfare and distance scenario to create a 96% confidence interval for the slope of the regression line. So once again, x equals the distance traveled in miles, y is the airfare. This is not required. Okay, this is not required for a confidence interval. We must define the parameters. We have to define the variables and a parameter. Beta 1, expected increase in airfare for every 1 mile in distance traveled. We've already talked about the conditions in the previous page. So I'm going to go ahead and run this thing. And what I said, it was stat test, scroll all the way to letter G, L1, L2, and my confidence level is 0.96, alpha trace. And I end up getting my slope. And here's my interval, 0.3307 to 0.12416. All right, 0.330 and 0.1241. What I'll notice is 0 is not contained. All right. Hey, 0 is not contained, and if 0 is not contained, then I actually have a true slope. Well, we know this was the slope the calculator gave us, 0.0786. And we need to know where this came from, the standard error of the slope. So this is slope plus or minus. This is your standard error of the slope, or your SB. And if I were looking at the table that goes with it, slope, standard error of the slope, you're like, that says standard error of the coefficient. It's standard error. but that value is standard error of the slopes, which is right here. But the question is, how do you get T star? Well, we want a 96% confidence interval. So we have to have a lower bound and an upper bound, and we want 0.96 here, and this is a lower, this is the upper. So what you do is go second bars, inverse T, parenthesis, 1 minus 0.96, close parenthesis, divided by 2. In degrees of freedom, our sample size was 18, and it's n minus 2 for degrees of freedom for regression. I know that's a little confusing, but n minus 2 for regression, press enter. And we end up getting 2.235. And there it is. So that's where our T star value came from. Okay, so we are 96% confident the true population slope for airfare relative to distance traveled lies within this interval. All right, and that's going to be your basic model. In repeated sampling, we expect that this method will capture the true population slope for airfare to distance traveled 96% of the time. But we could also note that because 0 does not lie within an interval, this slope is significant. We can say that there's evidence that this slope is significant because 0 does not lie within an interval. All right, so that was a long video. I appreciate you watching and hope to see you in the next one. Thank you.